Hello, everyone. This is lecture 23 of PTRE 451545 Advanced Drilling. And we will proceed today with module 4. And okay, Kalu was grading an exam for another class last night, so I didn't want to. I told him to prioritize the exam before the homeworks. That's why you are still waiting on homework for grade to go in, but it should go in this week, unless something out of the ordinary happens. He also has to grade another homework for the other class, so he's a little bit overwhelmed right now, hence the delay. But we really wanted the grades for the midterms of the other class, so it was like we had to prioritize that. Today I moved the office hours from 12 to 2:15, so it's only gonna be 2 hours and 15 minutes. Reason being, I have a meeting scheduled for 2:30, but I think that meeting really got cancelled, but they didn't officially cancel it. So I did send an email inquiring about that, and I did not get a response. So let me see, calendar 2022 of. Okay, I think there is no meeting today, but at 2:30. If there is no meeting at 2:30, I can potentially stay until 3 if there is people online waiting to see me. Otherwise, I have to cut short at 2:15. So I would suggest if you are going to join office hours today, try to do it early on. I'm always available by email email me, and we can schedule a separate appointment if needed, and the TA as well. If it's a question about the grading, I suggest you meet the TA first, because even if you meet me, I will send you to the TA because I don't want to interfere with the work that he's doing in a sense of he has to keep his grading consistent. I don't want to interfere and say, oh, you took 5 points from here and 3 points from there. It needs to be consistent with himself, basically, in all for all the students. So I cannot say, oh, you took 5 points from here, it's too much, because you can say I took 5 points from everybody, you know. Hello. Yes, sir. I'm not gonna go and tell him you took 5 points off, you should have taken 3, for instance. This is what I'm trying to say. Like, I trust that he does it consistently. And then I check everything, of course. If you guys have a question on the grading, you have to go to Kalu first. And he's it's a very easy to work with person. So I think you won't have an issue. If there is an outstanding issue, then come to me. But I cannot interfere with, I don't want to interfere with his consistency across all the students that he's grading. He needs to be consistent throughout all of you guys. I don't know how many of you are in the class. I think 11 or 12 is this class. Anyway, so office hours early today, and starting early and finishing earlier. I'm really sorry I have to cut them short. I have a feeling that the meeting would be cancelled, but yeah. What else? Okay, I posted the homework 5 is due on the 28th, and the part B of the project is due on 5th of May, which is the Monday of the last week of classes. I suggest you both start early. The homework and the project are very similar, so one helps the other. It's intentional that I put them. There is this overlap. It's very, very, one helps the other, and but they are time consuming, especially the project. The homework, start early, make progress every day, etc., etc. But the project is like a simulation. The simulation time, I did it on Easter Sunday. I went to very late at night because we didn't have class on Monday. I went to, you know, the long hall saloon.
Yeah.
You know that?
Yeah.
Ooh, I was there. Very late, and I was trying to do the project. And you know what kind of people you will see on Sunday night at these places.
Yeah.
So my mind was in a lot of places at that time, and I still managed to do the project. It's something like 8 hour simulation time, but you have the option to speed it up.
Wow.
Yeah. So I suggest the proper way of doing it. You're not going to achieve that in the first sitting. So I suggest that you start it and you do go a little bit, and then you stop, save it, open it again, progress a little bit. If you are in a good spot, save it. Maybe save it with a different name, because you might have a dummy, you may have an error that will stop the simulation, etc., etc. Sometimes the app is not amazing in a sense of it doesn't have very good matching with the operating system. Sometimes you just need to reboot the whole thing, like switch off the, not switch off the app, like close the app and open it again, stuff like that. So I would suggest you give it a lot of time and you start as early as possible. Now, granted, some of the stuff we haven't covered in class, but I have links to YouTube videos of simulations in the document I gave you, the project description, so that you guys are gonna be. Huh?
I'm greeting.
Oh, yeah. So you guys can help you. I mean, the videos I have, they are onshore cases, and this problem is offshore. But yeah, and then it's the groups that you are already assigning. They are either graduate students 5-for-5 and undergrad students 5-for-1. The 5-for-1 are gonna use a different method than the 5-for-5, but ultimately both methods work. Anyway, one is a 2-circulation method, the other one is a single circulation method. We're gonna go over them. And at the end, you both have to take that extra step of filling the marine riser with the kill weight map, which is extra. And I have a separate video for that. And that also takes time. And basically, beyond that, after you finish filling the marine riser, you also have to go back and drill through that problematic section and go through that. You have to pass through a target depth, which is where that kick formation, we call it, ends. Yeah, and at some point the simulator won't let you, it's gonna look like you are drilling, but it's not gonna be drilling anymore. Yeah, by the way, my simulator, when I lift the drill string, it shows it properly as lifting the drill string. I don't know, one of you had issues. It wasn't looking like you're lifting the drill string. So I was gonna suggest you close the app and you open it again. I was finding a lot of issues like that, and I was closing the app and opening it again. But this is how you learn. And the good thing about this is that you do it at your own environment. You can do it at home, you can do it at a cafe, you can do it in your office. You don't need to go to a separate classroom, rent a simulator, or like book the simulator, which is $100,000, fire it up. You know, complicated processes. So it's basically the same. That's why I think it's a very good teaching tool. This year, the project is a little bit harder than last year, but also the class, I think, is a little bit more, the averages of your grades are a little bit higher than last year. So it's good. Anyway, so where did we stop last time? I don't even remember. we talked up, huh? Huh?
Where we were discussing using the more density in place of the EMW to calculate the mass.
The mask, yeah, I remember that part. But I want to start a little bit earlier before that. So last time, I think we made it to this point here, slide 19. Well, slide 20, I guess. But I want to go over the steps because you're gonna be going through them before. So this is basically what we learned to do, and you have done already for part A of the project. By the way, part A of the project is still grading pending, so you will obviously have it back before you submit part B. So you start pumping, then you start rotating, and then you apply weight on the bead. Okay? When you stop drilling, you're gonna go the other way around. 3, 2, 1. Okay? You set the auto driller on, and now you are normally drilling, and you are looking for a kick. You are aware for a kick. Then, once you detect the kick, or you think you got a kick, you turn the auto driller off. Might need to press twice for it to stop. You leave the drill string a few feet off the bottom until you see the top tool joint above the BOP in real life. And then you go the other way. You stop rotating, you stop pumping, and basically this was removing the weight on the beam. Stop rotating and stop pumping. So we went the other way around, 3, 2, 1 now. And then once you make sure that you had a kick, indeed, you check for flow back, and you got a kick, you hit the BOP tab, and then you close the pipe ramp. You basically close the BOP, and then you need to always have a route for fluids to enter the well and leave the well. Okay, when you close the BOP, you don't have a route for the fluids to leave the well. Okay, I'm not saying the route exists, but the door must be closed if you have the well shut in. But the routes should still exist. So if you need to remove fluid from the well, you need to open the door basically. And how does that look like? You open the choke line. When you hit choke open, it basically opens the choke line, but the choke itself is on default 50% open in the app. So you need to go to the choke app, hit the rig gear on, so basically make it user ready, and you manually close the choke from 50% to 0. So the way it is like there is a route for the fluid to leave the well when the BOP is closed and the door is half open. You need to redirect the fluid into that route and then close the door. Why is the door half open? Is so that you don't make if you have it closed all the time at 0%, you are gonna have you have a potential to have a pressure blockage there, build up pressure there. You don't want that. You don't want to have hidden pressures on the surface for safety reasons. So they keep it half open by default when you are normally drilling. But when you are normally drilling, the mud returns from the flow returns line to the atmosphere. Now you close the BOP, fluid cannot go through the flow return line, but it needs to go out through the choke line. And the choke itself is half open, so you need to close the choke. Otherwise, you are going to be having fluid escaping the well. And then you are going to get the kick will become bigger and will become a blowout, even if the BOP is closed. So always have a route for the fluid to go in and a route for the fluid to go out. Now we're at step number 8. So in a sense, we went 1, 2, 3, and then 4, 5, 6 is basically 3, 2, 1. 7 is BOP closing, and then basically opening the redirecting through the choke line, and then step 8 is closing the choke itself to 0. Okay, and this is how it looks like. And I'm going through it again to make sure that this is clear. Okay, this is how fluid goes in the well. And now, normal drilling operation, this is how fluid comes out. Flow return line, atmospheric pressure. Okay, now I close the BOP. Still fluid can go in the same way as before. But fluid coming out, it cannot go through the flow line anymore. So it goes like through the choke line. Now you open the choke line, but fluid won't move out unless the choke itself is open. So by default, the choke is half open. And that's why you bring it to 0 to keep the well shut in. And you are going to open it strategically later. But this is how it comes out. You go in through the drill pipe, you come out through the choke line. Now, if we are going to inject, and you are going to have to inject to fill in the manifold, the marine riser after you circulate, you are going to do it through the kill line. Kill line is the other side of the choke line. It's thicker walls. It can withhold higher pressure. And this is how you inject, kill line. You can inject to fill up the marine riser as we're gonna do in the project, or you want to inject chemicals, downhole, stuff like that, during kick circulation. If you want to do bullheading, etc., etc., you are gonna do it through the kill line. Now, this is a common mistake. I have a route for the fluid to go in, as before. I don't have a route for it to go out. Okay, I have my choke line closed. I have my flow return line obviously closed because the BOP is closed. So fluid can go in, but it cannot come out. So if I make the mistake of starting to circulate now, I'm going to get an underground blowout. This is a common mistake that you can make, either in the simulator or in real life. And then you are going to have a blowout somewhere here at the casing shoe. And it's going to be very, very bad, very, very bad news. You need to always make sure you have a route in and a route out. And it's very easy to make a mistake. It's very easy to make a mistake. I make mistakes when I use the simulator sometimes. Anyway, you observe the SIDPP and the SICP with time, and you also observe and recorded the pit gain volume. We did that for part A of the project. By the way, part A of the project, what was your, what fluid do you think you had? What kick fluid was it?
I think it's, on my calculation, it's more of a medium crude.
Okay, what density kind of?
The density was 7.5 something, and the specific gravity is 0.907.
0.9. Okay.
Yeah,
so that was it. What kind of density was it?
Well, I went online, I searched for the density of oil and gas.
Yeah.
So in that range, they put that range to be medium density.
Yeah, but what kind of PPG?
PPG 7 point, I can't remember, 7.5 or 7.3.
I think it was 7.59.
Yeah, 7.59.
7.59. Okay.
Yeah.
I think it was, in real life, I think it was 8.77. It was actually water.
Wow.
It was a water kick.
Ah.
Yeah. It was a water kick. And I made that an intentionally water kick so that it will stabilize the pressure as well.
Okay.
A little bit lower than it was, I guess, was it 7.77 or 8.77, something like that. Bigger than water, salt or brine, basically.
The density of brine.
Yeah, I mean, something higher. so that it stabilizes the pressures. Otherwise, the pressures are moving. The thing is that many of you guys, I'm not saying that you specifically, but all the people online, some people were looking at that tab that says the predicted density of the kick, and that is really an estimation. You need to have an equation of state, and the equation of state is different as you go from gas to oil to water, etc., etc. So you guys, it can be very misleading. It can tell you it's gas, but it's actually brine in that case or something. 1 second, let me tell you exactly what it was. Okay. Tab A, open. 8.77 ppg.
That's answer.
Yeah,
I know.
that was the water. What was your equivalent density?
Equivalent density.
Yeah. The kilowatt weight.
The kilowatt weight was 9.32,
No.
10 point. I think I sent it to you on your email.
Yeah, but I didn't see.
You're talking about the kilowatt weight.
Yeah.
Yeah, with all the formation port pressure.
That's 11
Huh?
11.30.
That's good. Yeah, that's exactly what it was. So you got that one.
Yeah.
Then
I think the issue may be with the SICP and SIDP.
I think you messed up the pit game. Or you didn't wait for the SIDPP to stabilize.
It was stabilized.
Yeah.
Stabilize. So your FPP is fine, your kilowatt weight is fine, but what was your density? The kick density?
The kick density is 7.56.
No, that was too low.
That's too low.
8.77 ppg for me. Or what was it? But don't open that tab that tells you what they think.
Okay.
Yeah, also, that is what the app thinks the density of the kick is at the inside the well. You care about what is the density inside the reservoir. Yeah. And also you have to understand the difference between the two density values. 8.77 is the actual fluid. 11.3 is the pressure of the fluid converted to density. That's what you should have been using when you are drilling so that you don't get kicked, right? So those are two different things, okay? Two different densities. And this is what I'm trying to, yeah, but 11.3 was dead on. Dead on. That was Macondo, actually.
Okay.
But Macondo had, Macondo with the brine density of fluid, yeah. Anyway, kick column height. Okay, so you shut in the well. You are observing the SIDPP and the SICP and the pit gate at the same time. You have been doing that for your project. You hope that SIDPP stabilizes. If it's a heavy fluid comparable to your density, it will stabilize, but still not perfectly stabilized. For instance, now you have a density of fluid density of, sorry, mud density of 9.6, and you got an 8.77 kick in it. Okay, you know 8.77 is smaller than 9.6. It will be rising, but it will be rising very slowly. If it was 2 ppg and 9.6 the mud, it will be rising fast. There is a good chance SIDPP will never stabilize. And the YouTube videos that I gave you the links in the part B of the project, they are like that. They are very, very light gas kick. And it's basically never stabilizing because it always moves. It's like a balloon moving, a helium balloon moving up. So that's why I use Brian intentionally to make you guys make it easy for you guys for part A, so that you learn the app. So when you use it for part B, it's gonna be easier. So you want to estimate the FPP. This is the 11.3 value. So that has to do solely with the pressure of the formation. Okay, and from that you get the kill mat weight or kill weight mat. Same thing. Then you have to estimate the kick column height from the pit gain, etc., etc. By the way, this is active pit gain. Okay. You started from 500 barrels. You drill a few feet. And then you got a kick. So you have to estimate the pit gain from there. From the active pit gain, you can get the actual pit gain. You need to see how much you lost from drilling deeper, and then how much you gained from the kick, and then how much you lifted the bit of the bottom. So you need to, I think this is where you guys probably messed that up a little bit with the, you didn't get the, you probably got a very, okay, you got a low density value. That means the kick height was underestimated.
Maybe overestimated.
The pit gain, you got a pit gain lower than what?
The kick height, you got a 4.5?
I don't remember. I don't know. The kick height depends on every
Yeah.
simulation is different.
Yeah.
Did you take account of the fluid beneath the bit after you lifted it up? Beneath the bit, you have the whole hole filled with fluid.
Yeah.
Above the bit, you only have the ionidos filled with fluid. Did you take care of that? Probably not.
We did something.
Yeah, I think we consider that.
Yeah.
Yeah.
Okay, maybe that's what. I think you guys estimated, use the pit gain value that was smaller.
Our pit gain was around 13 points
Yeah, depends. It's going to be different for
for
everyone.
everybody. Okay.
Yeah. I'll be different for everyone. But the FPP, kill mat weight, and the density, these are the stuff that.
Why is around the density of the gas now lower?
Yeah.
Maybe I will look at the calculation again. Maybe there's an error in.
And actually, I think your SIDPP must be excellent because you got, and the SICP, because you got the FPP properly. So, and up to the kill mat weight, you are excellent. So it means that your SIDPP, your SICP were good. It's the pit gain
I
that you
think the
messed up.
problem probably around that.
Yeah, it's the pit gain.
Consideration, maybe you didn't consider.
Yeah. Is there the problem? Something, it must be geometric, or volumetric stuff, the issue. The rest must be okay. Okay. If it's gas or very gassy liquid, you have a problem, it's moving. Then you need to wait for the SIDPP to level off at a constant change or something. Then it becomes a little bit more complex. It's advanced really. But for liquid or heavier fluid as you had, the initial pit gain volume would be sufficient, along with SIDPP and SICP will stabilize. If it's a gas or something, sometimes you need to know pit gain, SIDPP, SICP at the same time. But yeah, for a heavy fluid, SIDPP will stabilize, SICP will stabilize, and then we are looking into the pit gain, basically. Also, you drill a little bit and then you got a kick. You need to take account of that losses in the active pit volume, right? When you are drilling, the active pit volume will go down.
Yeah.
Okay. This is what you need to do for the homework. This. And also, this is what I'm trying to tell you here. These are two different densities. One is the real density.
Mhm.
The other one has to do with the pressure.
Pressure.
Yeah. So it can be gas of very high pressure. It will have a very high rho kmw. Or it can be water at very low pressure. It will have a very low. But water is heavier than gas. Okay. Now, for the homework, which we might overview today or Thursday, you have the drill coral angular volume. If the pit gain, the original pit gain, which had to do with the kick that you received, is bigger than that, then your kick goes into the above the BHA as well. So you need to have a more complicated equation. Okay, we saw that. This is practical stuff, how much barite you need to mix. I hope you use these equations. Or if you are in the field, you have to use them. It's very easy. Even in the project, I'm expecting you to tell us how much barite you need to add, because this is what the math engineer will tell the people under him, how many sacks of barite to units to mix, etc., etc. And now you're gonna start circulating. You're gonna do the circulation at the rate that you determined earlier that you're gonna do it. And you will basically play with the choke as it happens, such that you don't take any more kick. You keep the BHP bigger or equal to FPP, slightly bigger, but not too big, too much bigger, so you don't fracture the casing shoe. Okay, and this is what you are going to do for the second project. We estimated, before we started drilling, we estimated the frictional losses at that 40 SPM. Did you do that for your project before you started drilling?
I think did we pump it then?
At 40,
At 40 and 100, normally this is what you need to do. So you know the frictional losses during before you get the kick, because you cannot do that during the kick. Okay, when you get the kick, you have drilled further.
Yeah.
So your well is deeper than what you did before you started, when you did that estimation, but it's not by much. That's the idea. Okay, in real life, they will measure the circulation pressure losses due to friction at 10, 20, 30, 40, 50, 60, 70, 100. So they have a lot of data they can play with later on. But for us, you just have the normal rate that you are drilling, we said 100, and then the slow for 40. Okay? Normally the 40 is company policy, like a standard process. Okay, good. That's the delta PX that we talked about. In part B of the project, because you already have the kick, I gave you the value. It was like 850 or somewhere there. Something like that. Then you add that to the ISIP, and this is going to be your initial circulating pressure. It's known as ICP. And then you will have a kill mat weight at the end, a new mat circulated in. You don't know the frictional losses at that new mat weight, right? You don't know it. So you are going to estimate, approximate it using this delta PX from the lower, and then the new mat, which is higher than the old mat. So if I'm telling you in the project of part B I gave you, I gave you 850 for the or something like that for the delta px. And your raw kill mat weight is 11.3. Your original mat was what, 9.6? Okay.
6.0.
Yeah, so you do 850 times 11.3 divided by 9.6, right?
Yeah.
Okay. And you're gonna find a value that is bigger than 850. If it's 850, I don't remember. Now, in real life, you don't see where the kick is. So you need to count strokes to see if you feel the well or not. When we say one circulation, in real life, it might be 10 circulations. Because they might be circulating for 2 days or something, or 3 days, just to make sure everything goes out. It's the real world. You don't see what's going on down home. How do they say? There was a guy who was saying, hey, it's dark down home. It's hard to see. So you don't know where and don't use that equation sheet from University of Texas I gave you because it has 42 at the bottom. You can use these equations. The first time I was teaching this class, it got me in trouble because I copy pasted those equations. Wow. And then I realized that the units don't match. It was giving me weird values when I was trying to get it. Okay. And then we should not exceed the mass because then you have an underground blowout. And the mass, normally, we don't include the pressure losses. Why we don't include the pressure losses? Because it makes the estimation higher. So it's like we have a built-in safety factor by doing that, right? So no need to also, you don't really care so much about the pressure losses on the annulus, from the casing shoe all the way up. It might not be as much. So if you don't have a value here, just go with this. But for the sake of circulation or sorry, it's always, I was wrong, raw mat, not KMW, my bad. And you're gonna play with the choke to keep the pressure within these values. You're gonna be looking at the SICP, not to exceed the mass. You're gonna be looking at the SIDPP, not to, the SIDPP, not to go under that initial value, so that you don't get more kick and you don't underground blowout. You are going to be playing with the choke until the kick gets out of the well and you have new mat all around. Then when you have new mat all around, what should be the reading on the SIDPP and the SICP?
New mod.
Yeah.
They should be the same.
How much? If the mat is correct.
If the mod is correct, it should be 0.
0, 0. Okay. What if you have no kick but the wrong mat? We said last time.
No kick.
No kick, but the wrong mat.
Wrong mod. Positive, but the same value.
Yeah, exactly. So, depending on these values, what you just said is important because there are two ways we can, oh, this is a new slide, I need to go. There are two ways we will do this kick circulation, okay? One involves two circulations, one involves one circulation, okay? Mass represents the SICP, at which the EMW in the annulus at the casing shoe depth is equal to P frac. The mat in the annulus can be the old mat or kill mat weight. It's unlikely that it will be kill mat weight. The goal is to circulate the kick out of the well, replace the raw mat with kill mat weight, the entire well, And this can be achieved with two methods, two main methods. One has two circulations, and we call that the driller's method, okay? First, you circulate with the old mud way to get the kick out. You get to the point that you said, where you have two positive but equal SIDPP and SICP, and they will be equal to what value?
At what point?
And when you get the kick out, and you have the one is shut in with the wrong mud, no kick inside. So they are equal,
They're equal.
equal to what value?
The SIDP.
The original
The
SIDP.
original SIDP.
Okay, so the SICP will change in that first circulation, and it will go eventually down to the SIDPP. It will go up and then go down. We'll see that in the homework. And then we do another circulation with the kill mud weight to replace the mud. And what would be the end? What would be the values at the end?
0.
0, 0 on each side. Okay, good. And the other method is the weight and weight method. I have a mistake. It should be weight and weight with a T at the end. Yeah, I will fix it. Okay, or engineer's method, you do it with one circulation. Okay, undergrads are going to use two circulation method. Graduates are going to use one circulation method in the project. They both work. There are scenarios where one might work better than the other, but as my old drilling professor used to say, regardless of where you are, the most important thing is the experience of the crew. If the crew is more experienced with driller's method, use the driller's method. If the crew is more experienced with weight and weight method, use the weight and weight method. Now, offshore, other cases, you may not want to use the driller's method for other reasons that we are going to see, but it doesn't mean that it cannot work. Okay. Other kick circulation methods are possible, like concurrent method, which is a hybrid of the two, loop and bleed, volumetric, etc., etc. And who knows, some of you may go to grad school and invent a new method. There is several ways you can do it. A driller's method and the weight and weight method are the more fundamental. Concurrent is like a hybrid of the two. It's a modified weight and weight method, to be honest. It's more close to this one than this. Several ways you can do it. Several ways you can do it. Okay, what is that? Well-controlled training using Drilling Simulator 3. The way I do it, to make it easy for students to understand, because it's a lot of stuff, a lot of details. It's an operations-based class. So I came up with two simulation exercises to help you learn. Okay, and they are about 15 steps, and we already covered 8 of those 15 steps. There are some differences from one to another, but if you do this exercise with, I guess, the default setting of the app, which is an onshore case, you are gonna like learn and be good to go. And I make you buy the app. I didn't want you to just use it for the project, so you use it to learn as well. And I suggest that you do those exercises before you go for well control certification as well.
Which exercise?
The one that we're going to see. You can also do the project again, but the project is a little bit of an advanced case of offshore. You have to do extra stuff. Okay, section A is what we already covered: drilling initiation, kick detection, and well shut in. We did that during part A of the project, right?
Mm-hmm.
Part A.
Yeah.
You did all that. Common for any method, 1 to 8 steps that we have already seen so far. Section B is kick circulation and mat column replacement by kill weight mat. Driller's method is steps 9, 10 for first circulation and steps 11 through 15, second circulation. Weighted weight method is steps 9 through 13, but is 1 circulation only. Okay, so we have 13 steps for weighted weight and 15 steps for 11 for driller's method. But the whole 1 through 8 is common, and we have already seen it, is what I have said at the beginning of the class. Okay, and I want to mention 1 second. Oh, sorry. You know, you don't know this movie, Any Given Sunday from 1999. It's an American football movie. And there is what's his name? Jim Brown, who was actually a very famous, I don't know if it was Jim Brown or the Al Pacino character who was saying that. Al Pacino was playing the head coach. And Jim Brown was a very famous football player. He was a running back, but he was very old times. He was playing for Syracuse University, and he was very good. But then he was, in the movie, he was playing the defense coordinator. And either of those two, he has a quote that he was telling the players that he was telling them, I don't mean that in a bad way, he was telling them that they are dumb enough, they made the playbook simple. They made it real simple. And it's a little bit like that here. You're gonna come back, you take this class, you come back 2 years later to review because you're gonna take the well-controlled certification. And the well-controlled certification is like that. You have to redo it every 2 years to be valid. It lasts for 2 years. Like I took mine in 2013, January 27, and it lasted until 2015, January 27. If I went back in 2015, I guess I was taking drilling classes still, but it doesn't mean I remember everything. So I need to go back and remember that. So I try to make this very, very simple. Ideally, you want to memorize those steps and know which one is following. So we make these steps as simple as possible. Okay, and this is how you need to remember them, as simple as possible, because when you're on a rig and something happens, I'm not saying that any of you is dumb, and I don't think that you guys are dumb, but you want to be thinking as simple as possible. Okay, so the next step is, okay, I started drilling, I got a kick, now I need to shut in the BOP. How am I going to do it? I'm going to shut the pipe ramp, the upper pipe ramp. Then what do I need to do? I need to provide a route for the fluid to leave the well. So it goes on like this. It's a very, very simple steps. I try to make these steps as simple as possible. And I forget them. And by the end of every class, every time I'm teaching this class, I remember them, you know. I force myself to remember them. And so you guys as well, okay? Steps number 1 through 8 is the same as we have seen before. It's basically these steps. Let me go back. This is why this morning I was telling you guys I need to review some stuff, go over some stuff that we already covered. This is step 1, circulate. Step 2, rotate. Step 3, apply weight on the bead. Okay, then you are looking for a kick. Step 4, remove the weight on the bead. Step 5 is stop rotate. Step 6 is stop circulating, right? It's very simple. It's very simple. Step 7, close the BOP and open the choke line. The choke line. Where it says choke in your Arabic means choke line. Now, step 8 is close the actual choke, right? Close that, and this is where we are now. You finish your part A of the project, and you're about to go to part B. This is where we are. So step 9, you are gonna reset the number of strokes to 0 because you don't see what's going on downhole. You need to see how far you need to not see. You need to understand how far you are when you are pumping. So you reset the number of strokes to 0, and you know how many strokes you need to go down and then up, right? You use those calculations with the 42 value. Now slowly open the choke while increasing the pump rate at small successive increments until the slow 40 SPM pump rate is reached. And you're gonna do it slowly until you get to 40. Now, don't do it having the speed multiplier on. Okay. And yeah. You know why?
No.
Because if you have the speed multiplier on the up times 15, and you are opening the choke slowly while increasing the pump rate, it counts like you do it at 15 times slower.
Okay.
So if you have a small leakage at that time, the pressure goes down a little bit. It goes down over a long time in simulation time. So make sure you are times 1, not in yeah.
Are we using this previous file? That's what we continue with.
Yeah.
The file we used for the first project. That's what we continue with now.
The file.
He's talking
The
about
file.
the file that.
No. I gave you a new file.
New file. Oh, okay.
And I gave you the FPP, and I gave you the kill mud weight, and I gave you a lot of stuff.
Okay.
Yeah, because everybody has to start from the same point, right? Otherwise, yeah. Yeah. We are gonna go over the. Wait, first we are gonna go over the homework, and then we are gonna go over the project, because we have to do this stuff so that you can start working on the project before you start working. Once the kick is circulated out of the well completely, slowly close the choke while increasing the pump rate in small successive increments until the choke is fully closed, the pumps are completely off, and the pumps, I should say, and the pumps are completely off. So you want 0% of the choke and 0 SPM. Now from 9 to 10, there is a big gap. Because yes, you are now circulating at 40 SPM and you are getting the kick out of the well. But at the same time, you are looking at the SICP not to exceed the mass, and you are looking at the SIDPP not to go under the original SIDPP, and at the same time you are looking at the SICP not to go under the original SIDPP, because then you get a kick. You are basically looking at the, okay, hypothetically, most likely throughout this process, the SIDPP would be constant. And the SICP would be changing as the mud is going up, as the kick is going up, sorry. You want the SICP to not go lower than the original SIDPP and not above the mass. So you don't get more kick and you don't get a blowout. So there's a big gap between those two. Once the kick is out of the well, and you are gonna see the flaring and everything, and then even then you are not sure that you don't have any more kick coming up. Right, in real. That's why you're gonna do in the real world, you might do 10 circulations. It might be 2 days between step number 9 and step number 10. But once you are certain you are done, close the pumps, close the choke slowly, and at the same time decrease the pump rate. So do the opposite of what you did here. I will show you in the video. You do the opposite of here. Here you open the choke and you start pumping. Here you close the choke and you decrease the pumping until you get to 0, and then you basically don't pump anymore. You need to have the choke closed. Sorry. Why do you have to have it closed? Because you have the wrong mud weight still. If you don't have it closed, you're going to get more kick. And who knows, when you are closing, you may not do it right and you get a small kick again. You are not really going to know it upstairs until the pressure stabilizes. Now,
Can I ask a
Yeah.
question? When we are circulating out to remove the kick,
yeah,
where will the mud flow out from once the choke is? Because you said the choke is completely short. Will it
no,
flow
when you
out
are
to the mud
circulating,
out?
yeah,
You want to get the kick out of the well now.
the choke is open
Okay, you have to open the choke. Okay.
to a certain level.
Okay.
Here, the choke is open. Slowly open the choke.
Oh,
Not fully,
okay.
slowly. You are opening it slowly and you are checking the SICP. Okay. If the SICP is getting close to the original SIDPP,
Close it.
you need to close the choke to increase it. If it goes too high, you open. Now, when the kick is moving up, it's going to be expanding. So it's going to be increasing. The SICP will be increasing. You need to be aware of that so that you don't do the underground blowout. So things are changing as you moving up. And in your homework, you are going to model that analytically. Mud column replacement using drilless method. Now we're in the second circulation. Change the mud weight, go to the kill mud tab, enable, click enable, set kill mud weight value, put the value, and then select the color of your choice for the new mud. Now the app is having some options for the kill mud weight. It's going to be a new color. It won't be gray as before. Okay, it can be what? It can be brown, it can be purple, it can be pink, it can be green. I use green because we are at UND.
Good.
And I always say only girls are allowed to use pink.
Wow.
Yeah. We had some, I think we had like 2 girls group in the first time I was teaching the class, and they both use pink, but it's really red. It says pink here, but it's red. Yeah, when I made those videos, I had already signed to be an instructor here. So it was fall of 2022. And I was using green because I was coming to UND, you know?
Okay. Wow.
Yeah. Anyway, so you set the new mud weight, kill mud weight. It's going to be higher than the original mud weight, you know that. And you set the color of your choice. Don't use pink if you are not a girl. And then now you enable the new mud weight. Okay, it's like you told your mud engineer, I need new mud at this value. And the mud engineer did those calculations on the variant and told his people, okay, mix me this much sacks of variant and this much water, or like diesel, etc., etc. And then I will repeat step 9. What was step 9?
That's nice to remove the kick.
No, the action with the pump and the choke. You open the choke
open it,
slowly,
yeah.
and then you pump.
Yeah.
You raise the pumping. You open it slowly and you pump. You open it slowly and you increase until you get to 40 SPM.
Yeah, 40.
Okay. And then monitor obviously the values. Now when you inject now, which side of the drill pipe side is changing or the SICP is changing? What you are, because before we said that the SICP is changing most of the time only. Now you're injecting down and then through the igniter, so both are going to change. First, you're going to see the SIDPP changing, going down to eventually 0, if it's correct. And then you are going to see the not zero, because you are going to be pumping. It's gonna go down from that value to the delta px times rho kilowatt weight divided by rho mass. Do you agree, Rocky?
Yeah.
Okay. And then you are gonna see the SICP change. And it's gonna change from that SIDPP original value plus delta px to don't forget the frictional losses, to basically 0, because by the time you make it out, it's gonna be 0. All the frictional losses are gonna be gone on the choke side, on the angle side. Once the entire mud column has been replaced with a new kill mud weight, decrease the pump rate to 0 in small successive increments. Basically, that's a repeat of step 10. But basically, I should say repeat step 10 here. Once the entire mud column has been replaced, repeat step 10. Same way. Okay, now I have my whole well filled with the proper mud weight, okay? And I stop pumping. So what should be my SIDPP value?
Should be 0 unless you trap pressure. If you trap pressure, it'll be whatever pressure you trapped.
That's correct. It should be 0 because I'm not circulating it. Yeah, this is correct.
And can I break in one other
Yeah,
pointer?
sure.
When you start with the kill weight mud, if you think about keeping the side of the U-tube constant that has a constant weight of fluid, so as the kill mud's going down the drill string, you keep the casing side constant. Once the kill mud exits the bit, you keep your drill pipe pressure constant.
Yeah, but it might not be possible if you have a gas kick, because the gas kick has the propensity to move on its own. If there is a big difference in the density between the kick fluid and the mud, you are basically fighting that buoyancy effects at the same time.
Oh, well, I just mean after the kick is out of the well for the second
completely
circulation.
out of the well.
Yeah, the second circulation.
Yeah, that's you're on the second circulation. Yeah. You are correct. So I guess I will change this to once the entire mud column has been replaced with a new kill mud weight, comma, repeat step 10. To make it simple, even simpler. And thank you, Justin. And then step number 14 is I go back, close the choke line, and open the upper pipe ramp. In your case, is upper choke because it's an offshore case, but no big deal. And open the pipe ramp. So I went the other way. When I was shutting the well, I closed the ramp and then I opened the choke line. Now I'm going the other way. I close the choke line and I open the pipe. I go the opposite. And I open the pipe ramp, right? Enable vent, enable open. I should mention that here. Enable, this is 2 steps. You click enable, vent, enable, open. To fix that. And then number 15, lower the bit to touch the bottom of the hole and proceed with resuming drilling operation. If you need it dry, it should work. Okay. If the kick fluid is gas, this is what I misunderstood what Justin said, and I thought it was the first circulation. If the kick fluid is gas, you have 2 key differences from a non-gas kick. The gas kick column has negligible hydrostatic head, potentially. So the kick column size is impacted by temperature a lot. And this is where you have to have an accurate, what we call EOS model, equation of state. The equation of state tells us how does the density of the gas will depend on pressure and temperature. Density of the kick as a function of pressure and temperature. So things are changing during the circulation. And also there is the buoyancy effects that you are fighting against. So the kick is moving as you are trying to make it move. So it's moving faster than what you are making, than what you are pumping. And it's also, density is changing as you are moving. So as you are circulating out, and you are in, oh my God, it's like creeping on you, you know? You are not comfortable. Many times during circulations can take days. And you do many circulations, somebody on the rig floor is making jokes, you know, etc., etc. It can really creep on you and make it a bigger problem. You need to constantly be looking at the pressures. And sometimes you may be waiting and not doing anything, and the pressures are changing. Sometimes both pressures are changing, just because the kick is moving very fast. And then you need to be manipulating the choke accordingly without even circulating. So it's very, very, it can be very, very bad. Okay. If you choose to neglect the gas density, assume that this is 0, this whole term is 0. So the height of the gas matters because this is basically taking part of the mass. Okay, that's why the SICP would be higher than the SIDPP at that point. And this is what you are dealing with. The height of the column above and below the gas kick is related by this equation. I think you understand that. Fairly simple. You have the height above the kick, the height of the kick, and the height below. All together, TVD. Right?
Mhm.
Okay. You understand that. The shut-in pressures become, this is the left side of the YouTube model. You don't have any kick in the YouTube model. Are they waiting?
No.
No. And then you have the right side of the YouTube model. Right? Okay. And you know these equations. You combine the two, you get this for SICP. Because you recognize that this part is basically what is it? This TVD is basically H above, H below, plus H above plus H below plus H gas. Now you take the H gas out, so you are left with H above plus H below. So the TVD goes away. Okay, fairly easy to understand. Let me just write it here to avoid confusion. TVD equals H gas plus H above plus H below. So you have this and this now. And you assume that rho gas is equal to 0. So this ideally would have a different, another one here, minus 0.2 rho gas H kick, but this is 0. So it goes away. This goes away. That's why you don't see it. Okay, and now we have, I guess, you combine them together, and then you recognize that you can take basically, you can input SIDPP there. We prefer you doing that because SIDPP is an easy value. You can read it from the surface, okay? You can read it from the surface, plus 0.052. Raw mass minus raw gas. You can ignore the raw gas, okay?
Zero.
It will be 0, and then you have raw mass basically, plus H gas. You cannot ignore H gas. You cannot ignore H gas. And how do you get H gas from? PK. H gas. H gas is not 0. This can be 0 or close to 0. Yeah. Don't ignore H gas ever. And then if you set the raw gas equal to 0 again, you simplify into this. And then you have everything that you need except the H gas, everything you have from the surface, SICP from the surface, SIDPP from the surface. Raw mat, you know what is the raw mat. You control it, right? H gas you don't control. How do you get it? Pit gain. Pit gain divided by all the stuff that you need to divide it with. The gas volume is calculated using the angular capacity opposite of the drill pipe and or drill collars, such that, what I was saying earlier, the volume of the gas from the pit gain divided by the angular volumetric capacity, or you get the height of the gas. It doesn't need to be gas, it can be kick. It's still the same process, okay? Same thing as you gonna do in the homework. Okay, C angular, that's the capacity, which you know how to calculate. Using the YouTube method, now that I have the gas kick. Now this V gas is in what units do you think?
The V gas is what?
What units do you think it's gonna be?
That's barrel.
Barrel, yeah. Yeah.
Volume.
Very nice. Okay. Barrel divided by the capacity of the annulus. I should make that C.
Then
Barrel per feet.
yes.
Yeah.
Barrel cancel barrel.
It's the volumetric capacity. Some people use V for it, but I try to use, I would change that. Yeah, it's a mistake. It should be V angular. C angular, sorry. C angular. So you have barrels divided by barrels per foot, you end up with foot, tall, height. Using the YouTube method, the pressure on the top and bottom of the gas key column, P gas, considering the mat column height above it, H above in feet is the following. So this is the pressure of the gas at the top of the gas key, okay? I think it's easy to understand from the YouTube model, right? The right-hand side. You take the right-hand side of the model, of the YouTube model, and you do this. You do this. Where is it? Okay. I do SICP plus how much this weighs. Okay. Now, if I want to go here, I do SICP plus how much this weighs plus how much this weighs. How much does this weigh if the density of the gas is 0?
Is 0.
Okay, so the pressure here would be the same as the pressure here,
Yes.
right?
Yes.
Okay. You understand that, right?
Yes.
Okay, you understand that? The pressure here, if the density of the gas kick is 0, is the same as the pressure here.
Yeah.
Okay. Donald, do you understand that?
Yes.
Okay. It is important. That's why I'm asking. It's a weightless kick. Worst case scenario. So recalling Boyle's law from physics, you remember Boyle's law? Why is that?
Yeah, I remember.
Okay.
Pressure and volume are inversely related.
Yeah.
Yes.
Well, a more
At
advanced
a
version
constant
of it.
temperature.
Huh?
At a constant temperature.
Yeah, but if I have the temperature in, it will be like this. But for our method, this is the original pressure when the gas was in the reservoir, in the rock. This is the new pressure when the gas is at the kick, the gas is at the inside the well. This is temperature before, temperature now. I'm gonna actually assume they are the same, so they're gonna cross out. And then the peak gain initial is the volume before, as soon as we got the kick. And the V gas now is the volume now, as the kick is moving up. I assume that once I got the kick, and the kick is at the bottom of my well, its pressure is the same as the pressure it came from the reservoir, and the volume is the same volume as the original peak gain, right? Okay. And the pressure would be FPP. And then it's gonna be moving up. Pressure will be changing to basically according to the Boyle's law. Okay. So I will simplify things. Isothermal, this goes away. Okay. That's one simplification. And then substituting the expression for V gas from the previous slide, I get this equation. Remember the expression from the previous slide was this. P gas, oops, sorry. SICP plus, SICP plus 0.052, rho map H above, okay. And then V gas is this, SICP minus SIDPP. So I come here, okay, I have a value for this, C annular SICP minus SIDPP. What was the bottom? I don't remember. Huh?
I actually can't remember.
Yeah. And then V gas is something else. Sorry, I was wrong. V gas is that value with the C annular, the fraction. And P gas is the long equation. So 1 second. This is V gas. This is P gas. Take those, put them here, rearrange, and you get this. Okay? Now, I want to solve for SICP. That's why I have it in bold. This is the variable I want to bring to the left. Okay? I want to bring it to the left. And then I get, remember that this equation from the math for quadratic equations. Okay. I will end up with this. I want you to be able to derive this equation. Yeah. Every step of the way. And I will tell you why. Because this number 4 is not this number 4 here.
Number 4.
Is not the same as this. And it's a complicated, but you can follow through. I want you to be able to derive these equations. Because this is what you are going to use in the homework. But in the homework, you have the slides available and you can do it. I want you to be able to derive it. Okay? And understand what it means. It basically models how SICP will vary during this first kick circulation. And this is when SICP is at initial value, that's when the height above the kick is h above comma I, C angular I, VP gain I, h above I, SIDPPI. I assume that normally SIDPP will stay constant, but it might be changing. And then, oh yeah, okay. Okay, thank you everyone. I will talk about it on Thursday. But you can start the homework and we're gonna go over it then. Thank you, have a nice rest of your day. Office hours are early today. Thank you, Donald. Recording.